Okay, we're broadcasting and see if, and just, we generally start about 5 minutes after, 2 to 3 to 5 minutes after the hour, so let people sign up, sign on, okay?
Mm-hmm.
Yeah.
But there's nobody signed on yet, or can I see the participants? Or
About 30 people right now, okay?
26, 28.
oh, okay, there you go.
Mm-hmm. So it's been about 90 degrees Fahrenheit here for the last 3 days. It got up to 98 in Newton the other day. Really miserable.
Yeah, we're really nice here. We haven't had any hot days yet, so we're very lucky.
Well, that's good. Yeah. Yeah.
But it's fire season, so there's always that.
Yeah, that possibility. Yeah. Yeah. Art Palmer says it's a lovely post-rain run this morning he had. Okay. Did you go to Central Park, Art?
Bob, I'm in Rocky River, Ohio, living with my mother for the month while my sister, who lives with her the other 11 months of the year, gets a vacation. Now,
Okay.
the main problem is my sister's up in northern Maine, and she called yesterday to say she found a lovely house for sale. And I reminded her that she's supposed to come back. So about 2 miles away from my mother's house is Rocky River Reservation, which is a park that follows the Rocky River for further than I've ever run.
Okay. Well, that's good. That's good.
And way fewer people than in Central Park. So much less of a mask issue. You have to pull the mask up, maybe 5 or 10 times in the whole run, whereas in New York it's constant. There's so many people.
Mm. Yeah, yeah. No, when I've been going out walking up Heartbreak Hill a lot, just
curse it for me.
Huh?
Curse it for me.
Oh, it's a wonderful hill. We live about a mile from it, and but there's a lot of traffic on there's what they call a carriage road right next to it, which is mostly bikers and walkers and runners. And but there's a lot of traffic, and you have to have a mask all the time, really. So it's yeah. And then up at the top, there's a little thing called Mount Alvernia Academy, which is a small Catholic school, grade school, which you can add that on to the elevation. So it's a nice walk. It's a nice climb, actually. So you should try that next time you're here, Art.
I should take a diversion off the marathon and run up the hill for some extra distance, get to the Catholic school.
Yeah, and there's 2 or 3 extra loops I can tell you about. I'll send you a map, all right, that you should, they're actually they would be quite good.
And the problem with Heartbreak Hill in the marathon isn't that the hill is so steep, but it comes at the worst possible time in the marathon.
At mile 20 when you're out of glycogen, right.
Yeah, and to do well in Boston, once you get over Heartbreak Hill, the last 10K is downhill. So to run a good time, you have to get over the hill and then recover enough to really go fast the last 10K. And that's brutal. I've never succeeded at that.
You broke 3 hours, didn't you?
Yeah, but at the bottom of the hill, I was on 250 pace and I finished in 258.
Okay. Yeah. Okay, another minute or so, and then we'll get going. Okay.
Bernd, how are things in Europe?
It's probably not as bad as in the US, so we're slowly recovering. And I think Europe is probably the only continent where the number of infection goes down at the moment, and I hope it stays like that. And it would be great to see you guys again, but wear your masks, right, and to try to bring the numbers down. But I think we are fine, right? So we are working in shifts, and well, in particular in the offices, we should avoid to be more than one person per office. So a lot of people work and analyze the data at home, but on the wet lab it's actually okay, since air circulation is good, and I think we can continue working almost like as normal. But
well, we're back this week to essentially everybody working, but at any one time there has to be 50% density, so it shifts. And again, everything that can be done at home, like data analysis, you have to go home and do data analysis. You can't hang around the lab looking at your spectra. But as far as getting in to be able to do lab work now, except for the shift issue, the fact that you have to be on shifts, it's relatively normal. The problem for New York City, of course, is if people from other parts of the country come to New York and bring the virus back, because we're hovering just below R0 of 1. So it won't take much to get R0 above 1, and then before long we're back in catastrophe.
Oh, yeah. Okay, Kong, why don't we get going, all right?
Yep, sure.
Yep.
Let me share my screen. Okay, I'm assuming you all can see my screen. Nope, it's not this one. So greetings to everyone. Good to see you all again, on the participant list at least. Thanks for staying with us for the past 3 or 4 months, and it's my pleasure again to give you a weekly update on Zoomina that I always give every week. So if this is your first time here, please subscribe to our mailing list, because this is where we will distribute the news and make announcements of the future speakers. And also if there's any update on the Zoomina, if we are going to continue it, or if we are going to change it to bi-weekly event, or if there's a change of date or time because Bob has to teach, then we will announce it through the mailing list. And if you are interested in listening to our past sessions, and you can find it on our group website, don't worry about taking a snapshot, because I will copy and paste this in the chat room, and then I will talk to you about the Q&A. Then you can ask the questions anytime during your talk while the speakers are presenting, or after the speakers are finished with their presentations. But if you do want to ask a question, I would like to ask you to use the Q&A function that you can see at the bottom of your Zoom window. And then if your question is too long, or if you're not familiar with the Zoom interface, feel free to raise your hand, and then I will allow you to speak so that you can ask your questions verbally. And lastly, don't use the chat function, because most likely I will not be able to see your questions. And then also the speakers might not be able to see it unless they look at the chat. So all the Q&A, they are safe and they are stored in our Dropbox. So if you want to look back, if you want to have a post-Zoomina discussion, feel free to look at the Q&A on the Dropbox, and you can comment on it. And we try to keep these things go on so that you can always look back. So I will copy and paste this in the chat room, and then I will pass the session to Bob so then he can introduce our speakers today.
Okay. Well, thank you, Kong. And today we have 2 really outstanding, excellent speakers who are going to talk about really quite different topics. Is Monica Blank from CPI in Palo Alto. Monica was an undergraduate at the Catholic University in Washington, D.C., I think. And she did her PhD here at MIT with Richard Temkin, who's been a longtime collaborator of ours on the dynamic nuclear polarization experiments. Monica then worked a little bit at the Naval Research Lab in Washington, D.C., and in 1999, she moved out to California and joined Kevin Felch and his colleagues in the GYROTRON research group at Communications and Power Industries. And CPI, it's a very strange name. It used to be called the Microwave Tube Division of Varian Associates, okay? So it's something that should be very familiar to people in NMR spectroscopy. And then the second talk will be by Bernd Reif from the Technical University in Munich. And he will be talking to us about proton-detected NMR, magic angle spinning with sensitivity. And I'll tell you a little bit more about Bernd when we introduce his talk. So Monica, the virtual stage is yours to share your screen and get started. Okay?
Sounds good. Share and slideshow. Okay, thank you very much for the invitation and for the opportunity to make this talk. I'm representing a few different people. We have a small gyrotron group here at CPI, formerly Varian in Palo Alto. And we've had the excellent fortune, the really good luck of being teamed up with Bruker for the past 15 years, teamed with them in their endeavors to open a commercial market for DNP gyrotrons. And so we work particularly with Melanie, Rose, and Leo Tomatich, but really dozens of people of Bruker, at Bruker over the years. So I think I'm going to try to start the talk by discussing several different potential millimeter wave sources for DNP. I don't always like to admit it, but there are other DNP sources besides gyrotrons. So we can go through a few of the other device types in the state of the art, then delve into DNP gyrotrons. And then I have a couple of slides on some future directions for DNP gyrotrons, and then a short summary. So solid state sources, millimeter wave solid state sources are available, and they have been used and they continue to be used for DNP. Some examples are impact diodes, gun diodes, and then a little bit more recently, there are these frequency multipliers, harmonic multipliers. That's a Virginia diodes example. And solid state sources can make, you know, tens of milliwatts at hundreds of gigahertz. And they're very compact, they're very easy to use, but as you go up in frequency, their power capabilities drop off precipitously. And if you're working down at 100, 200 gigahertz, maybe a solid state source is perfect for you. But as you go up, you might need just a little bit more power than a solid state source can provide. So the next in line is conventional vacuum electron devices. So some examples of conventional devices are like a EIO, extended interaction oscillator, or extended interaction klystron. Some of these are made by our sister division, CPI Canada. Also pictured on the right, clinotrons, which are a kind of backward wave oscillators, could be used for DNP. So conventional vacuum electron devices can make, you know, 1 watt or tens of watts at hundreds of gigahertz. CPI Canada will sell you a 20 watt EIK at 263 gigahertz. And the clinotron has made really impressive, like 100 milliwatts at 545 gigahertz. So they really have a lot more power capability in the hundreds of gigahertz than solid state does, but sometimes you need even more power for even higher frequencies. So then you can move into gyrotrons. That's what I work on. So gyrotrons obviously can make tens of watts or even kilowatts or megawatts at hundreds of gigahertz. The gyrotron as a device was literally invented to make high power in the hundreds of gigahertz range. At the time it was invented, it was for fusion applications, but of course many other applications have grown up over the years. So these are 3 examples of some pretty high-end gyrotrons. Over on the left, this gyrotron resides at Fukui University, but it was made in a collaborative effort between Russia, Japan, the Ukraine, and Bulgaria. That's a bit of a flag test. Do you recognize the flag of Bulgaria there? But that's a really impressive gyrotron that made 5 watts at 770 gigahertz. In the center is a Fukui University record breaker that broke the terahertz barrier. And both of those gyrotrons are sitting in their magnets. On the right, we have one of our gyrotrons that made 50 watts at 593 gigahertz. It's not sitting in its magnet, so it's not actually so much smaller than those gyrotrons. It's just missing the magnet. But gyrotrons are where you have to go when you really need high power or you need some power at really high frequency. So all of these devices have pluses and minuses. And even to this day, I mean, solid state is a completely relevant source for DNP. So on this chart, green means good, red means bad, and yellow is in the middle. So solid state is extremely compact. There are really no lab requirements. There's no high voltage. You don't need any cooling water, but you can really only make tens of milliwatts at hundreds of gigahertz. So the cost of solid state sources is pretty low, but I like to think in terms of cost per watt. So if you have to pay $30,000 for a 30 milliwatt source at 400 gigahertz, that's $1 million a watt. That's actually quite high, if that's how you want to look at it. In the middle, conventional vacuum electron devices are still actually quite compact. Those millimeter wave EIKs are about the size of a coffee cup. There's some lab requirements. They often need water cooling. There is high voltage, it's enclosed, but there's high voltage around. So now you have sort of more of a lab device. They can make, you know, medium power. The cost is definitely higher than solid state, but less than a gyrotron. And the cost per watt has come down. It's not $1 million per watt anymore. Now, you know, you're hundreds of thousands of dollars per watt. And then moving over to the gyrotron, of course, the size and weight is not good. The gyrotron sits in a superconducting magnet. It's huge. It definitely has lab requirements. We would use 10 kV, 15 kV, again enclosed, but still. You need water cooling, sometimes compressed air. But if you want to make tens of watts, hundreds of watts, kilowatts, it's really your only choice in the very high frequencies. So the cost is higher. It's actually not that much higher than an EIK, but it is higher. But the cost per watt is the lowest of all. So that makes us look better. But the bottom line is, if you really, really want a couple hundred watts at a terahertz, you don't have any options. So you just have to somehow overcome the negatives of the gyrotron and focus on the positives, because that's really your only choice. So I'll get into gyrotrons a little bit. And specifically talk about what I know best, the family of Bruker second harmonic gyrotrons at 263, 395, 527, and 593 gigahertz. So why can a gyrotron make more power than a conventional vacuum electron device? Is it because gyrotron people work harder or smarter? I'd like to say yes, but I don't think that's true. It actually has to do with the device physics. So all vacuum electron devices basically are the same. They're not really that different. So they all need a source of electrons. Back here, that's the electron gun. They all need a space for the electrons and the electromagnetic wave to interact, some type of cavity or structure. Then after the interaction, there's this electron beam that has to be dissipated. So they all need some kind of collector. It's a vacuum electron device, so it's in a vacuum. We have to have a vacuum envelope. And that means you have to have some type of window for the microwaves to go out from the vacuum into the world where you need them. So all vacuum electron devices, klystron, EIK, helix GWT, gyrotron, they all have these components. What separates them is this region where the interaction takes place. So you can't just have a bunch of electrons hanging around an electromagnetic wave and expect them to exchange energy. It doesn't work that way. You have to create some type of resonance. So I live in California. I like to think of it in terms of surfing. So when the surfer is out in the ocean on his board, if he's just sitting there, the wave goes by and he just goes up and down. There's no energy exchange. He doesn't get propelled into shore. So when he wants to ride the wave, what he does is he gets on the board and he paddles. He tries to match his velocity to the velocity of the wave. And when he does that, then he and the wave can exchange energy and the wave will propel him into shore. So this is an excellent example of beam wave resonance, surfing, but it's actually a bad example for a vacuum electron device because it's the opposite. In my example, the surfer is the electron and he's getting energy from the wave, but of course that's more of a particle accelerator situation. In the vacuum electron devices, the electrons, the surfer, give up their energy to the wave and amplify it. So the details of how this resonance is achieved is what separates devices. So conventional vacuum electron devices have to do something to the electromagnetic wave. The electromagnetic wave has a phase velocity that's the speed of light. the electrons are not traveling at the speed of light, and you need some way to slow that wave down to match the velocities. So in a slow wave structure, a vacuum electron device conventional structure, they use some mechanism to slow the wave down. They have a complicated structure, a helix GWT, you force the electrons around this helix like that. But what that means is the structure of the interior of this device has to be of size on the order of a wavelength. So as you go up in frequency and your wavelength's getting very small, your devices are getting minuscule and your power capability severely drops off. So that's what happens. That's why an EIK can only make 20 watts at 263, and it probably can't even make 1 watt at 400 gigahertz. But a gyrotron works differently, completely differently. It has a very different beam wave resonance from any other device, and that's what enables it to make the high power. So I'm going to explain a gyrotron to you in one slide. After this slide, you can go out and make your own gyrotron, because I'm telling you, it's that easy. The gyrotron works from something that we call the negative mass instability, which is really the relativistic dependence of the cyclotron frequency. So the cyclotron frequency of an electron is the charge of the electron times the magnetic field divided by the mass of the electron times the speed of light times this relativistic factor gamma. And if you put in the numbers, the constants, that works out to about 28 gigahertz per Tesla. So if somebody tells you they're making a 280 gigahertz gyrotron, you know they need a 10 Tesla magnet. You can work at harmonics of the cyclotron frequency. They might need a 5 Tesla magnet, but at the fundamental, it's 28 gigahertz per Tesla. And it works as shown down here. So if you have a group of electrons that are the red dots labeled 1 through 8, and you have a magnetic field going into the page, by the right-hand rule, the electrons are spinning around that magnetic field in the clockwise direction. If you also have electromagnetic wave with the E field shown by those green lines, then what happens is, let's take electron 3 here. Electron 3 is accelerated by the electric field. And so it moves a little bit out in gyro radius, and it picks up relativistic mass. So it slips back in phase and moves towards position 1. On the other side, the exact opposite thing is happening. Electron 7 is being decelerated by the electric field. So it moves a little bit in phase and, moves in orbit and goes forward in phase because it has less relativistic mass. So in this way, a gyrotron forms a bunch sort of at position 1, and the electrons are spinning around and the electromagnetic wave, the green, is spinning around, and you get a resonance and you make the exchange of energy. And so it's all done with the magnetic field. There's no slowing down of the wave. There's no circuit feature that does that, and it's all about relativity. When I go to a cocktail party and somebody tells me, I don't know what relativity is, and I don't know what it means, I tell them, oh, I wouldn't have a job if it wasn't for relativity. It's all about relativity for the gyrotron. So what this translates to is the ability to make a macroscopic circuit even when you go to high frequency. And I have a very graphic example of that on the next page. So these are to scale the circuits for 3 different 94 gigahertz gyrotrons that we have made and sold at CPI. On the left, we made a TE01 mode gyrotron amplifier at 94 gigahertz and 10 kilowatt average power. The circuit size was 0.195 centimeter radius. We also made a 30 kilowatt device using the TE02 mode at 94 gigahertz still, and the circuit radius was twice as big. And then over there on the right, we made a 2 megawatt device, still at 94 gigahertz, and the radius is more than 10 times what it was back here for our low power device. So with the gyrotron, your circuit size is not dictated by your frequency. You can always go to higher order modes. That does not come for free. There are difficulties with higher order modes, but we know how to solve those difficulties. So this is on one page precisely why a gyrotron can make high power at high frequencies. It's not mandated that the circuit is shrinking when the frequency goes up. So the gyrotron interaction is extremely strong. I promise you, if you have a source of electrons, a pipe, and a strong magnetic field, you will get a gyrotron interaction. The details of exactly what mode, what frequency, how much power. Okay, all of that you have to be careful about. But the gyrotron interaction is so strong, it cannot be stopped. So we take advantage of that. And Bruker has opened up a commercial line of gyrotron-based DNP spectrometers, DNP tools for spectrometers, and they're installed all around the world. They have more than, I think, 45 installed. And this is just sort of a collage. Maybe you recognize your facility in one of these pictures. But I'd like to draw your attention to the bottom right there. That's the highest frequency to date. That's a 900 megahertz spectrometer with a little teeny 593 gigahertz gyrotron there, and that's at Lausanne. So our gyrotrons look like this. They are, after all, vacuum electron devices, so they have all the same components. We use an electron gun. Our guns tend to operate 15 kV with 1 or 200 milliamps. Our interaction cavity is here. The magnet is not shown on this page, but the interaction cavity sits right at the high field region, the peak field of the magnet. And then there's some space in between. So that's where the magnetic field's ramping up and the beam is being compressed. Then this is actually the 593 gigahertz gyrotron for the 900 megahertz spectrometer. It works in the TE14-3 mode, which is a very complex mode, and it's useless. You need to really have a Gaussian beam to transport across the room to the NMR machine. So we have an internal mode converter that consists of a launcher and a couple of mirrors, and then this last mirror directs the generated 593 gigahertz right out the window in a direction perpendicular to the magnet axis or the axis of the gyrotron. And then we have this collector for the spent electron beam. And over on the right, you can see the solid model. That's what it looks like. All the components gunned down at the bottom, this little cavity in the middle. That's our aluminum oxide window, collector up here. And this gyrotron is about a meter tall, and it weighs about 20 kilograms, 25 kilograms. So I have a photo of that gyrotron in test. We do use the second harmonic with all of our family, the Bruker CPI family of gyrotrons. So if you're doing the math in your head, you know, that would be like a 22 Tesla magnet for 593, 28 gigahertz per Tesla, but we're using second harmonic. So Bruker made an 11 Tesla superconducting magnet that's refrigerator cooled. The gyrotron is sitting in here. It's kind of hard to see in that big, huge magnet, but it's there. The collector's up top, and these are the cooling inputs. The window is back here, and for all the gyrotrons, we have a sort of not permanently attached, but mostly permanently attached little unit that houses one piece of waveguide that makes it very easy for Bruker installers to connect the transmission line. So that's the gyrotron in test. I have some typical results that we get. This plot shows output power in watts. You'll have to forgive me if I say kilowatts or megawatts, because most gyrotrons that we make are megawatts. So sometimes I'll say megawatts, but for DNP, it's always watts. But output power in watts, I'm glad to see I put just W, versus cathode voltage in kV. And this plot actually has curves for all four gyrotrons in our family. The blue curve is 263 gigahertz, green is 395, 527 is in red, and the 593 is in black. Bruker asked us to make 50 watts for the lower frequency gyrotrons. They actually asked for just 40 watts from the 593, but we can make 50. And you can see that in every case, the power can be tuned smoothly from full power to basically zero. And that's really important because you don't know in advance exactly what power is going to saturate your enhancement. So you're going to always need the ability to move power around as you do different samples, different preparations, whatever. And you can also see that even though I bragged that the gyrotron can do whatever frequency, whatever power it wants, it is actually a little bit harder to make power with a given cathode voltage, a different and beam current. It's harder to make power at the higher frequencies. And that's because of a lot of effects, because at higher frequencies, mechanical alignment is getting more important. Also, ohmic losses in our cavity are going up at higher frequencies. So the gyrotron has the ability to make whatever power you want, sort of, at least for spectroscopy, but you might need a bigger power supply. All 4 of these gyrotrons use the exact same power supply. So we didn't have any more input power available, and that's why we made a little bit less power at 527 and 593. Power can also be tuned by keeping the cathode voltage constant and you changing the beam current. That's a little bit slower tuning, but it can be more efficient if you have reasons to want to keep the efficiency high. So these curves show similar tuning, output power in watts versus beam current in milliamps for a constant voltage. So for Bruker gyrotrons, we have to, provide a variety of tuning curves, all kind of information about the frequency that has to be very precise, the frequency stability. And then another important aspect is the output beam. We generate a Gaussian beam, and it has to be a very high quality Gaussian beam because it's going to be transported many meters across the lab to the next magnet, the NMR magnet. And it will, there will be miter bends in the transmission line. There are various components. So we have to prove the quality of the Gaussian beam, which we do with infrared images in planes at increasing distances from the end of that corrugated waveguide. So this is just a pictorial example, but of course we do a mathematical fit, and our Gaussians tend to be 98%, always higher than 95%, the desired beam. You can see that the crosshairs, that circle and crosshair, represent the center of our window. So even out 23 inches or 3/4 of a meter from the guide exit, we're still dead on the center, aligned with the center of the window. So it's a very good Gaussian beam, and it transports in the corrugated waveguide very well. So this is a fun picture. It strikes fear into the hearts of people who make conventional vacuum electron devices. Bruker asks us to run the gyrotron at full power and just put a piece of metal at the end of the waveguide, run into a dead short, reflect 100% of the power back in. So if you tried that with an EIK or a Helix GWT, the device would be destroyed. They actually have interlocks to prevent returned power, but the gyrotron is kind of big and spacious in there, and it doesn't mind at all. So we run that way for 30 minutes, an hour, and demonstrate that there were no faults and that there was no damage to the gyrotron. That's just a fun fact about the strength of a gyrotron. Right now, CPI isn't the only place that makes DNP gyrotrons. They're made all over the world, and people are doing a lot of research and working on a lot of different topics. So some of the interesting directions that gyrotrons for spectroscopy and for DNP specifically are going. Everybody wants higher frequency, higher harmonics, amplifiers are of interest, so I have a few words on those. Higher frequency, well, yeah, sure. As NMR goes to higher frequency, DNP has to follow along. As one example, unfortunately, we don't have a complete design. I can't show anything, but at Bruker and CPI, we're working on a 790 gigahertz gyrotron for their 1.2 gigahertz NMR. And, one critical part is the 14.5 Tesla magnet. We are working at the second harmonic. And there has to be a negotiation between the gyrotron makers and the magnet makers. The gyrotron people would like a 1 centimeter long flat field in a, let's say, 10 centimeter long cryostat with a 10 centimeter diameter warm bore. And the magnet people cannot do that. They would like a 1 meter long magnet with a 1 millimeter bore. And so we have to have a big round of compromise and negotiations to figure out some overall system that will work for both parties. We both have to give and try to push ourselves to the limits of our technology. So that's us. Based on the strength of our 593, the ease of making that gyrotron, we felt we were more than justified going up a next step in frequency to 790. But of course, around the world, people have been working at a terahertz and even more for a very long time. So I didn't mention it formally, but the group at Fukui University in Japan, alongside with MIT, have been pioneers in this field. They've been the leaders in the field alongside MIT for a very long time. In Russia, they work on DNP gyrotrons. Russians invented the gyrotron, so they can do anything. They're very good. In Europe, there are at least 2 groups in Switzerland, 2 separate groups working on gyrotrons. in China at UESTC and even Peking University. They have very smart, good people working on DNP gyrotrons. In North America, of course, there's us. There's MIT, who did the groundbreaking work, the first people who applied gyrotrons to DNP almost 30 years ago now, 30 years ago. And there's Bridge 12, which I think a lot of people on this call know. So we're far from special. We just kind of got lucky to get teamed up with Bruker, but we came into the game kind of late. And there's very many groups, a lot of research on gyrotrons, specifically for DNP and for spectroscopy. So people are going up in frequency, and there really are no hard limits for the frequency of a gyrotron, but the magnet starts getting pretty tough and pretty expensive. So we did use 11 Tesla for our 593 gigahertz gyrotron. Let's say you wanted a 1.5 gigahertz, you had a 1.5 gigahertz NMR and you wanted a DNP with it, that'd be a 988 gigahertz gyrotron. If you use the second harmonic, that'd be an 18 Tesla magnet. Obviously, it can be done. I mean, that's you have a 36 Tesla magnet sitting across the room for the NMR, but that's a big cost, an 18 Tesla magnet. That's a big cost. So you can't talk very long about going higher in frequency with gyrotrons without also talking about higher harmonics. Higher harmonics are extremely attractive. So that same 1.5 gigahertz NMR that would use the terahertz gyrotron, at second harmonic, it would need an 18 Tesla magnet. I'll do the math for you here. At third harmonic, it would need 12. At fourth harmonic, it would need only a 9 Tesla magnet. A child can make a 9 Tesla magnet, that's easy. But the high harmonic does not come without a cost. People have made third harmonic gyrotrons and even higher harmonics at millimeter wave and terahertz frequencies. They've done it, more than one group, but efficiencies decline precipitously with increasing harmonic number. And I think before you ask your gyrotron maker to make you a fourth harmonic, you need to think about the overall system. So absolutely, your magnet gets much simpler. But if your efficiency gets so low that all of a sudden you need, let's say, an 80 kV beam and you need 500 liters per minute cooling to cool the collector for this beam, then maybe the overall system with the simpler magnet, but the more complex gyrotron isn't a winner. So you really have to think about it. There are tricks to maintain some efficiency as you go to third and higher harmonics, and people know them, but there are costs. There are costs. So you can tell I'm not that interested in going above second harmonic, but I know we'll be asked to very soon. So the third area people are working are gyrotron amplifiers. Gyrotron amplifiers have been around a long time. Actually, the first gyrotrons were conceived as amplifiers. We make gyrotron amplifiers for radar here at CPI, and we have for a long time. So for DNP, amplifiers are of interest for several reasons, not really just one. I remember in Xander Barnes's talk, he talked about chirping the frequency. So amplifiers have not only instantaneous bandwidth where you can use whatever frequency you want, but you could chirp extremely easily. And then another way that maybe not everybody thinks about, if you want to do time domain work, then you need short pulses and fast pulsing. So if you're trying to pulse even 20 or 30 kV very fast, that doesn't work that well. That's actually a very complex and expensive pulsing system to get your high voltage up and down and up and down. If you're using an amplifier, you can leave the beam of the gyrotron on and just turn that probably solid state drive source on and off. And it's very easy to achieve short pulses and fast pulsing, kilohertz, 10 kilohertz, whatever you need. So amplifiers have a lot of advantages, but they are a little bit more complex. Here I'll advertise for MIT a little bit. They've done the most work on amplifiers for spectroscopy. This is a photo of a 140 gigahertz gyrotron amplifier that MIT made. It made 550 watts at 1.2 gigahertz bandwidth, which is excellent. And that's Alexander Sohn in the picture. And they did a separate amplifier, 240 to 260 gigahertz, that made almost 50 watts with an 8 gigahertz bandwidth, which is excellent. And that's Emilio Nani in the picture. He actually now works at SLAC, just right behind me over there, down the road. But amplifiers are definitely an option, but you know, like harmonics, they come with a cost. They're more complex, and quite frankly, not to bash solid state, but if you're up really high, you know, 700-800 gigahertz, and let's say you have a 100-watt gyrotron that has 30 dB gain, you're going to need, you know, a lot of milliwatts that I don't even know if solid state can provide with that kind of bandwidth. So gyrotron amplifiers are always of interest and should always be worked on, but they're still maybe not quite in the ready for commercialization stage, except for ours, for radar. We're ready for commercialization, but not for DNP. So I didn't pay attention to the time, but I'm about ready to conclude with summary and outlook. So I hope you've gathered that gyrotrons are under development and in use for NMR and DNP all over the world. And I think it's fair to say that gyrotrons are absolutely the best source option for really high field NMR and DNP. If you're at lower fields, you can use solid state, you can use other vacuum electron devices, but to go up really high where you need tens or hundreds of watts, you really have to use a gyrotron. Gyrotrons, because of their basic design, their basic physics, have a unique ability to produce high power at higher frequencies. Gyrotrons have demonstrated more than terahertz, it's not a problem. And I argue, not everyone accepts the argument, I argue that there's a modest cost per watt compared to competitors. So Bruker has exploded the commercial gyrotron-based DNP market, and they have more than 45 systems with our gyrotrons installed around the world. In the future, I'm sure everybody's going to be looking at higher frequencies. I know we are. You can't talk about higher frequencies without talking about higher harmonics, and amplifiers are always there, always poised to take over. So I think the future for DNP gyrotrons is really exciting and always challenging. And I hope that you're as interested in it as we are. So I guess that's all I had.
Okay, whoops. So I can't get back on the air here. All right, thank you, Monica, for a really very, very nice talk. There are 4 or 5 questions here to begin with. The first one from Siri down at Florida State. He wants to know if gyrotrons can operate at second, third, so forth harmonics. Could you do the same thing with an EIK or an EIO or other vacuum devices?
Absolutely. It's difficult, but there are absolutely higher harmonic slow wave devices. Yes.
Okay, and the next question from Christian Griesinger in Göttingen. He wants to know if there are DNP probes ready for narrow-bore magnets since you're working towards or for 1.2 gigahertz, right?
Yeah, I'm just the gyrotron guy. That's really a question for Bruker. I assume that's a yes, but maybe a Bruker person could raise their hand because I can't speak for them.
Melanie, you want to answer the question?
I just allowed Melanie to talk. Melanie, please.
Yeah, so the standard bore DNP probes are under development, and that would go up to 1.2 gigahertz. At this point, we don't see any technical showstopper. So similarly to the 790 gigahertz gyrotron, all the work so far hasn't shown any technical challenges that says it can't be done. Of course, it's a matter of time. But the standard bore probes are in development for 800 megahertz up to 1.2 gigahertz.
Okay, so Christian, you need to order a couple of probes for your.
Yeah. I mean, we just got our 1.2 today, and that's why this is a really actual question.
Timely, yeah.
So Shankun Gao has a couple of questions. He wants to know how you determine the position of the electron gun with respect to this cavity center. And also he wants to know, does the output power increase infinitely with voltage? So you run up the voltage even higher, would you get more power?
Okay, so position of the electron gun. I did not explicitly say it, but if you were really paying attention, you might pick up that the gyrotron only interacts with the perpendicular energy of the electron beam. You know, the beam is spinning around. So there's axial energy of the electron beam, but we can't take that energy. We can only take the perpendicular. So this relates to where is the gun. So the electrons are born at a certain magnetic field, and then they travel towards the cavity. So the field's increasing and they're spinning up. At some point, they have too much perpendicular energy, and they don't have enough axial energy to make it over that magnetic field into the cavity, and they turn around and go back to the gun. So we position the gun based on its geometry, the voltage we're using, and the magnetic hill, so that it has that right perpendicular energy in the cavity. Usually the magnetic compression for a gyrotron like this would be 25 or 30. So if you're sitting with a 10 Tesla magnet, you have 25 times less field at the gun. So we have to put the gun wherever the magnet maker tells us that field is going to be. And that's why our gyrotron looks funny, why it's so long down near the gun and so short up near the cavity, because they have sort of a long space there between the high field region and where the gun is. On the voltage, the answer is all sort of yes. It depends on your operating point. Okay, higher voltage in general means higher power. But if you're sitting at one magnetic field and one beam current, you reach a point where the interaction, you actually start to give back the energy to the electrons. You over bunch sort of. And so you cannot sit at one point, increase voltage forever and get more power. But you should be able to change the other parameters so that at higher voltage you can get higher power. Yes.
Okay. Jeff Reimer from Berkeley wants to know something about FELs, free electron lasers. Are they too difficult or complex to use for DNP?
Probably, but you know, the FEL is a close cousin to the gyrotron. It's not that different. FELs have notoriously low efficiency, so they might be a bit big, but sure, all device types are welcome. And FEL, it can definitely make power at high frequency. It is a candidate. Sure.
Now, there's an FEL being constructed at Santa Barbara
Sure.
with the idea of doing DNP. Yeah.
Oh,
By
good for them.
Yeah.
Yeah, they tend to be really broad frequency too, so they're very useful.
Could you get some, and Fred Mintic wants to know if you could get some examples of issues with high harmonic gyrotrons.
Oh yeah, well, we didn't really get into it, but the interaction strength is going down with harmonics. Like the bunching isn't as good, you can't extract as much energy, but on top of that, so you've got, let's say, this somewhat weak third harmonic interaction. Unfortunately, the second harmonic and the fundamental interactions that are right next door are not weak. So when you try to make a high harmonic gyrotron, it's sometimes very difficult. Even if you're willing to put up with the low efficiency, it's difficult to access exactly the third harmonic or fourth harmonic that you want without accidentally getting the fundamental and the lower harmonics. Because like let's say the 14.3 mode is about the 1500th cavity mode for real. Like 01 mode is the lowest, 11, 02, 22, 32, count up. There are 1,000, 2,000 other modes that could be excited. So you have to place your beam very precisely. And those harmonics are low interaction strength, but the lower harmonics and fundamentals are strong, and you tend to excite those. There are ways to select out the mode that you want, but really getting exactly that high harmonic that you want without getting all the low harmonics next to it is the main problem.
Okay, and the final question is, what is limiting the realization of several hundred watt gyrotron for DNP?
Nothing. We're at CPI actually a for-profit company. We're not really much profit maybe, but we don't have the luxury building devices that we're interested in. We sort of have to build devices that people ask us to build, or to put it bluntly, pay us to build. So Bruker has asked us for 50 watts, and we make 50 watts, but it's no problem. The gyrotron cooling, the mode choice, several hundred watts are easy. And actually at 263, we can make more than 100 watts, even with the 20 kV, 200 milliamp power supply that we have as part of the system. So that's not a problem. It's just what Bruker wants.
Okay.
Yeah, maybe can I just ask a quick question? Actually, I thought I was just curious. Like for the 9.4 Tesla 263 gigahertz, if I'm not mistaken, you are using the second harmonics, n equals to 2, and then like the theoretical efficiency is 1 over n squared, so it's only 25%. But in principle, for the magnet that you use, you could have built a first harmonic, and then you can get a lot more efficiency. And why not do so? I'm just curious.
Well, we did start at 263 with the fundamental, but then Bruker kind of wanted to standardize the product line. So they built basically one magnet. I think it has extra windings maybe when it's going to be used, but the cryostat is the same for the entire product line. And I think to make their business model work, they had to standardize a bit. But there are 9 fundamental 263 Bruker gyrotrons out there in DNPs. And there was actually a photo of one of the photos in my collage was for a fundamental. So I glossed over that because it didn't fit with my story, but thanks for bringing it up.
So does the fundamental one like give a lot more power compared to the second harmonic?
It's higher efficiency, absolutely, because even at the second harmonic, your efficiency is going down. So, we're down by almost a factor of 10 in efficiency just to go to the second harmonic, and you'll go down 10 more to go to the third.
Okay, thanks.
Well, there's one final question. It says, can a gyrotron be clubbed with the NMR magnet? In other words, could you put the gyrotron in the NMR magnet?
Absolutely. People talk about this, and there have been some, at least, conceptual designs. No problem. It's an engineering feat because the gyrotron needs to have certain magnetic fields at the gun, which we just discussed because of the excellent question, at the cavity and at the collector. And if your magnetic field is not shaped right, how is your device going to be? How does it work? So there are some difficult details to be worked out, not to mention that there's already something else in the bore of the NMR magnet that you need to occupy the same space as. But definitely several groups have had this idea and explored this idea. Again, not us, we weren't asked to, but it's feasible. It's absolutely feasible. Okay,
all right. Well, listen, thank you very much for an excellent talk. Lots of questions, interesting things for people to think about. Our next speaker is Bernd Reif from the Technical University in Munich. And Bernd was a graduate student with Christian Griesinger. He then was a postdoc here at MIT for a while, and then he moved back to Germany, first to Berlin at the FMP with Hartmann Ashkenaut and company, and then to Munich, where he currently is professor in the chemistry or biochemistry department. Today he's going to tell us about proton detected solid state NMR and sensitivity and resolution. So Bernd, the virtual floor is yours, right?
Okay, thanks, Bob, a lot for the kind introduction and for the invitation to be able to present some of our data with you. In our group, we are working on different topics. So the major topic that most of the co-workers work on is actually protein misfolding. We would like to know what is the structure of an amyloid, and we would like to know how these amyloids actually interact with small molecules and molecular chaperones. And for this purpose, we perform solution state as well as MIS solid state NMR experiments. And in the context of the chaperones, we are also interested in large protein complexes, and particularly small heat shock proteins that can interact with these misfolding proteins. And we are also interested in proteasomal and ribosomal complexes, also for proof of principle, how far we can go with solid state NMR methods. But the topic that I would like to talk about today is NMR methods, in particular proton detection, because I think this is also the most suitable topic for the audience today. And the story started for us like 15, 20 years ago, approximately, where we thought about proton detection experiments. Obviously, the protons would be the ideal nucleus because in comparison to heteronuclear detected experiments like in 15, we potentially gain like a factor of 30 in signal to noise. At that time, proton detection was not done a lot because actually it comes at a price. So typically when we did proton detection at that time, we had to deal with very broad lines. And this was due to the fact that all the protons talk to one another and we're just